Welcome back to Unit 4, Section 3. Today we are talking about proving some items in the, triangles in the coordinate plane and proving other theorems. So we're going to go ahead and start with proving triangles in the coordinate plane. In example 1 here we have given points D, E, and F and points G, H, and I. Prove that triangles DEF and GHI are congruent. And then when it says state why, that is in our proof. So we don't actually have to write out any sentences because it's already in our proof. The first thing that you need to do is plot those points. I already have them plotted on mine, so you might need to pause and catch up. I'm going to go ahead and start by identifying, I'm going to use the Pythagorean Theorem here. So I'm going to find the triangles. I'm going to create right triangles for each side and find the distance that's traveled horizontally and vertically, and then we're going to do a little bit of math. So I have, well, it's all math, but we're going to do some algebra. So I'm going to start on my orange triangle. I'm going from I to H. I go up 2 over 1. I'm going to go from H to G. I'm going over 2. I accidentally drew one too many lines there. We'll take that off. And we are going down 1, 2, 3, 4 squares. 1, 2, 3, 4. And then I'm going to go from G to I, and I'm going over 1, 2, 3, and up 2. We'll go ahead and draw that in. So I went over 3, up 2. And now I'm going to do the same thing with our green triangle. So I'm going to go from F to E, and I again go up 2, over 1, and then E to D. I'm traveling 4 vertically and 2 horizontally, and then I'm going over 1, 2, 3 and up 2, over 3, up 2. Alright, so now I have all of that information. I do need to show their value, so I'm going to do that work to the side in just a second, but you might be recognizing that I have 1 and 2, 1 and 2, 2 and 4, 2 and 4, 3 and 2, 3 and 2. Which is good because that means that our segments are actually congruent, and we already know that, but we do have to show the numerical value too. So I'm going to go over to the side here, and I'm going to start with HI and EF. So I have HI is equal to EF, which are both equal to, we have our Pythagorean Theorem, a squared plus b squared equals c squared, and then to solve for the distance, you have to square root it. So what you really have is the square root of a squared plus b squared, and that is going to be the answer to these two things. So I'm kind of jumping ahead a little bit. If you need to review the Pythagorean Theorem, Khan Academy is a great place to look. So I have 1 squared plus 2 squared. And that simplifies, so I have 1 squared is 1, 2 squared is 4, 4 plus 1 is 5, so that is the square root of 5. And both of them have that numerical value, so they're congruent. And next, I'm going to go from E to D and H to G, so I have HG is equal to DE, or I need to go in the same direction, so that's ED. And both of those are equal to the square root of 2 squared plus 4 squared. And my square root symbol is a little large there, so I'm going to fix that. So I have 2 squared plus 4 squared. 2 squared is 4, 4 squared is 16, 16 plus 4 is equal to 20. So I have the square root of 20. Alright, next I have DF and GI. So I'm going to say that GI is congruent or equal to DF, and both of those are equal to the square root of 3 squared plus 2 squared. 3 squared is 9, 2 squared is 4, 9 plus 4 is equal to 13, so this is the square root of 13. And all of those things have the same value, and they travel the same distance, same shape, same size. That means that our segments are congruent. So in my proof, the first 3 lines of this proof are actually just going to be writing my congruence statements, and there's no given statement on this. So I have, in my first 3 lines, I have EF is congruent to HI. I have DE is congruent to GH, and I have DF is congruent to GI. And I know I flipped the order on those a little bit from what's written there, but they're the same thing. So if you would like it to be the same, you can copy it down so that they match. And the reason for all of them is the definition of the word congruent. So we have definition of congruent. Definition of congruent. Definition of congruent. All of them. Okay, so because we now have 3 sets of corresponding congruent sides, I can go ahead and say that I have 2 congruent triangles. So I can say triangle FED is congruent to triangle IGH by the side-side congruence postulate. All right, we're going to go ahead and take a look at example 2. Example 2, you might notice, only has 2 lines. So this is going to be a little bit of a shorter proof than we've previously had. So in example 2, it says to prove that the triangle with coordinates at -2, 4, which I'm calling A, 6, 4, which I'm calling B, and 2, -3, which I'm calling C, is an isosceles triangle. So in order to show that something is an isosceles triangle, I need to show that I have 2 congruent sides. The base doesn't have to be congruent, but the sides have to be congruent. So I'm going to go ahead and I'm going to start by finding the length of the base. And to do that, I'm just going to count the squares. 1, 2, 3, 4, 5, 6, 7, 8 squares, so that is 8 units long. If it is an isosceles triangle, the base doesn't have to be the same size as the sides. I just need to prove that these 2 sides are congruent. And I'm going to do this by showing a little bit of algebra as well. I'm going to zoom in here and we're going to again create a right triangle so that the hypotenuse is what's left, and we're going to find the length of AC and of BC. So I have from A to C, I traveled 1, 2, 3, 4, 5, 6, 7 squares. And I traveled 1, 2, 3, 4 squares horizontally. And then I'm going to check from B to C. So I go 1, 2, 3, 4, 5, 6, 7 that I traveled down, and 1, 2, 3, 4 that I traveled in. And we do need to write these out separately, even though on the last one we took a shortcut, but we're going to write them separately because we need to see what the actual result is, and if we were able to show that BC was congruent to AB, then we don't need to show that it's congruent to AC. But I think you can probably already tell just from looking at this that AB is not our congruent side. We're looking at AC and BC, which we've also kind of mentioned. So we're going to go ahead and to the right, we're going to show that AC is equal to, again, shortcutting the Pythagorean Theorem. We have 7 and 4, so I have 7 squared plus 4 squared, which is equal to 7 squared is 49, 4 squared is 16, 49 plus 16 is 65. Forgot what the number was there. So I have 65 that I'm square rooting, and then BC is equal to those same things. So BC is equal to the square root of, again, 7 squared plus 4 squared, which is equal to square root of 65, which means, and this is going in my first line, that AC is congruent to BC by the definition of congruent, because they're the same shape and same size. That numeric length tells us that. Because we have now shown that we have 2 congruent sides of the triangle, I can then say in my last line of this prove that I have that triangle ABC is isosceles by the definition of isosceles. Because we're not trying to prove what an isosceles triangle is, we're just trying to prove that this is an isosceles triangle. And it is, because we have two congruent segments on, so just two congruent sides. And now that we have shown a couple examples of proofs in the coordinate plane, we're going to go ahead and flip the page, and on example 3 and example 4, we're going to prove a couple theorems about triangles. All right, here we are in example 3 that says to prove that the base angles of an isosceles triangle are congruent. So you probably already noticed I added a couple things here. Both of these examples are going to have some pieces you need to write in real quick. First, we have given that AB is congruent to BC and D is the midpoint of AC. Prove that angle A is congruent to angle C. So the reason why we have those statements is because when it says that we're trying to prove that the base angles of an isosceles triangle are congruent, we're trying to show that the angles on the bottom of the triangle, the base, are congruent to each other. And it's an isosceles triangle, so by definition it is, but we have to prove that. We can't just say it. So we're going to go ahead and go through this proof. And I'm going to start once again with my given statements, and I'm going to put those in my first two lines this time. So I have AB is congruent to BC. Because it's given. And I have that D is the midpoint of AC by, again, the fact that it's given to us when we started. All right, so now that we have two given statements, there we go, we can go ahead and look at what we already know in our image from that information and what's in the image. So the first thing I notice is that this picture has a line that's connecting the two triangles, this BD, segment BD. So I can go ahead and say that BD is congruent to BD because of the reflexive property. So that's the first thing I'm going to say. I have BD is congruent to BD by the reflexive property. And right now I'm noticing that if I'm trying to prove that two triangles are congruent, because that's going to help me out, if I can say that the triangles are congruent, then I can say the pieces are congruent. So I'm going to start by trying to show that these two triangles are congruent. If I know that this side is congruent to this side and this side is congruent to itself, my options for proving two triangles are congruent are currently side, 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 or side, angle, side, because those are the only two shortcuts that have two sides involved. So I'm going to look at this a second, and I have that D is the midpoint of AC. That gives me information about the other two sides. So I don't want to use side, angle, side because I only have information about sides. So I'm going to go ahead and write in my next line. I have that we have D is the midpoint, and because D is the midpoint, that means that AD must be congruent to DC. So I have AD is congruent to DC. I'm going to go ahead and draw those tick marks in my image, and I know that because of the definition of a midpoint. And now that I have shown that I have three sets of congruent sides, I can say that these two triangles are congruent to each other. So I can say that triangle ABD is congruent to triangle CBD by the side, side, side congruence postulate. And now that I know that my two triangles are congruent, then I can go ahead and say that my two base angles are congruent. So I can say that angle A is congruent to angle C by the CPCTC corresponding parts of congruent triangles are congruent. So therefore, these two angles are also congruent. And I'm going to go ahead and put those markings in there. I've shown what I needed to show. All right, let's take a look at example number 4. Example 4 says to prove that the points on a segment's perpendicular bisector are equidistant from the segment's endpoints. So if we're trying to show that they are equidistant, that means that I need to show that this segment LP is congruent to this segment MP. So that's really what I'm trying to show. I did write in a given statement here that says that JK is the perpendicular bisector of LM. That's something that we know because we have a perpendicular bisector there, and that matches our image. So I'm going to go ahead and start once again by adding in my given statements. So I have just one given statement this time. JK is the perpendicular bisector of LM. I'm going to go ahead and write that down. JK is the perpendicular bisector, and there's actually a symbol for that. It's an upside down T. That means specifically perpendicular bisector. I think I might have accidentally said just bisector the other day. It's perpendicular bisector, so that's what you should be using it for. So JK is a perpendicular bisector of LM, and that is given. All right, so now that we have that given statement, we're going to go ahead and look at what we know in this image. I am recognizing that since this is bisecting, I have two sets of congruent sides right there. And I also am noticing that this is in both triangles, so I can also say that PK is congruent to PK. And those are two things that I can write down. I'm going to start with the reflexive property here, so I say PK is congruent to PK by the reflexive property. And then I'm going to, well, actually I'll draw in my tick mark there to show that that is congruent. And now I'm going to go ahead and draw in my tick marks for LK and KM, because I said that those have to be congruent as well because of the fact that PK is bisecting LM. So I can say LK is congruent to MK by the definition of a bisector. And it does say it's a perpendicular bisector. We don't need to be that specific with our segment pieces, but we do have to be really specific with the next line. So in the next line, I'm going to write in that because we have a perpendicular bisector, that means that we are cutting through our segment at a 90-degree angle. So both of these angles have to be right angles. And because they are right angles, they are congruent. So I can say that angle PKL is congruent to angle PKM. So that's my next line. Angle PKL is congruent to angle PKM. If you want to be really specific with the symbols, there is a symbol for right angle, and you can use that there too. I'm not going to show it to you. You can Google that one. So that we know because of the definition of a perpendicular bisector. So this keyword right here, perpendicular bisector, is what lets us know that we have the two congruent angles. So I have definition of not just a bisector, but of a perpendicular bisector. All right, so now I have shown a side, I've shown an angle, and I've shown a side. So because of that, I can say that my two triangles are congruent by the side, angle, side congruence postulate. So let's go ahead and write that down. Triangle PKL is congruent to triangle PKM by the side, angle, side congruence postulate. And now that I have shown that I have two congruent triangles, then I can go ahead and say that PL is congruent to PM by, or actually wrote that backwards in the drawing, either way. So we can go ahead and say LP is congruent to MP by the CPCTC. Once again, corresponding parts of congruent triangles are congruent. So therefore, all pieces of these two triangles have to be congruent because we already showed that those triangles are congruent. All right, this is where we are going to stop for today's video lesson, and this is actually our last section in this unit, so we will be working on some review and then we'll be taking our test. Right now we have that scheduled for Thursday the 19th and Friday the 20th, depending on which class or which day you are on. So make sure you are preparing for that. There are a lot of proofs in this section, so you need to make sure that you're spending some good time looking at those proofs, because it is a good portion, if not the whole amount, of your test. So just make sure you are preparing well for that, and if you are needing some additional help, you can come in before or after school, or you can email me and I will get back to you as soon as I can.